Hello friends, myself Vikash and today I am dealing with the experiment of digital signal processing laboratory entitled filter design using pole zero placement method. So aim of the today's experiment is to design a suitable filter using the pole zero placement method to remove the baseline wonder error from the given noisy PVG data. So what is exactly pole zero placement method? This method is used for the purpose of designing the frequency response of the narrow band filter. And the basic criteria of filters are as follows. Frequency active filters such as low pass filter, high pass filter, band pass filter, band stop filter, etc. Digital oscillator and digital oscillator, and finally notch filter and hall filter. The transfer function of any filter could be written as in this form, where capital N represents the total number of zeros, capital N represents the number of poles, G is the gain of the filter, and Z of k and P of k are the roots of the numerator and denominator, basically the zeros and the poles of the transfer function H of Z. So, what are the rules for pole zero placement method to design a filter? Firstly, the location of poles and zeros affect the frequency response of the system, as discussed in the previous slide, as in the form of its transfer function. Zeros on the unit circle at a specific frequency reduces the magnitude response at that frequency of the transfer function. The poles on the unit circle at a specific frequency magnifies the magnitude response at that frequency of the transfer function. So from point 2 and 3 we can conclude that the poles and zeros have a negative effect on each other. And there are some constraints which are required to be followed while using this method to design filter. Firstly, we should place poles inside the unit circle to ensure the stability of the function. Otherwise, if you place it outside, the HFZ tends to become infinity, that is very large. And zeros can be placed at any location in the Z. And the second, when using complex poles and zeros for designing, we should work with conjugate pairs rather than single poles or zeros, as this results in real coefficients for our final differentiation of the filter. So the first question of lab is to remove the baseline wonder having the cutoff frequency of 0.4 Hz from the given until PPG data of 10 seconds using a suitable filter designed using 40 method, and the sampling frequency of the data is 18 Hz. Since we have to remove the baseline frequency which goes up to 0.4 Hz from the PPG frequency range of 0.5 Hz to 5 Hz, so we can simply do that using a low pass filter with cutoff frequency 0.4 Hz. And so the desired transfer function of the filter would be as mentioned, where G is the gain of the filter as discussed previously, and all other values are mentioned here, which is calculated using the relation between cutoff frequency and sampling frequency. So applying inverse unit transform in H of Z, we get the difference equation that is as follows. Now we will implement this difference equation on Arduino platform to get the filter through which then our noisy data will be passed and move to baseline error. So this is the Arduino code for so. Here this is the formula which I used for designing the difference equation of the filter, and x of I is the noisy data and y of I is the noise baseline error free data. So let's see the plots. So as you can see that the red colored line is the noisy PPG data, which is having baseline wonder, which is seen in the form of this small curve, basically a small frequency involved. And this blue colored line is same PPG data, but with no baseline wonder error. As you can see, it is moving straight along the zero axis line. So our data, PPG data is now free of baseline wonder. And the second part of the question is to synthesize an artificial baseline wonder error with frequencies 0.1 Hz, 0.2 Hz, and 0.25 Hz, and add it to the clean PPG signal. So now to remove the added baseline component, we'll use a previously designed filter and check its accuracy by estimating quantities such as mean square error, root mean square error, and SNR, which is calculated immediately. And sampling frequency is still 80 Hz. So these are the formulas which I are going to use to calculate MSC, RMSC, and SNR. So for this purpose, we are going to use a clean PPG signal in which we are going to add error and then verify our algorithm by removing the same. Since all the baseline frequencies are less than 0.4 Hz, so our designed filter would be successful. At 0.4 Hz is greater than all three, 0.1, 0.2 Hz and 45 Hz. So here we have did the same thing, and additionally we calculated the MSC, RMSC and SNR. Let's see the output of this. So as you can see, so this is the blue color line in both of the figure is the baseline boundary frequency which I took in form of sinusoidal wave. This frequency is 0.1 Hz, 0.2 Hz, and in the next page 0.25 Hz. And here the red color signal is the PPG data plus baseline frequency, and the green color data is the clean PPG signal. As we can see, there is slight sinusoidal deviation from the mean axis of blue color data, which is due to baseline error. And finally, when it is removed, it is going along the straight line in both of the cases. Similarly, we can see here the green color is clean, red color is PPG data plus baseline error, and blue color is baseline error. Though there are some little bit of baseline error here because of high amplitude of baseline frequency component. And finally, we calculated the MSC, RMSC, SNR and got the result as MSC equal to 0.01, RMSC which is nothing but the square root of MSC which is 0.12, and SNR and dB is plus 19.32, which is suggesting our filter is excellent. So thank you for listening. Goodbye.